All right, welcome everybody to our second session of Seabird University. And again, my name is Genevieve Howell. I'm the Director of Products and Global Services for Seabird Scientific. And I'm here to walk you guys through our service and recalibration process. All right, so what you are seeing on the screen here is Point Nemo. So this is marking a point in the Pacific Ocean that is so far removed from land and civilization that the closest humans to this spot at any given time are most likely to be astronauts. Which I think is really cool. There's more than 1,000 miles of ocean in every cardinal direction. And it's a really nice visual for understanding and thinking about not just on the surface, but then you think about the depth of that ocean. It just really underscores how much is unexplored, how much we still don't know, and how much the work that we do really matters. For us, being able to support the kind of science that really helps us understand our climate better, the impact that climate change has on our economies, our security, our health. All of that is important work, and Seabird has a field-proven track record of being able to deliver CTDs and BGC sensors that have the accuracy and the stability and the robustness to really be able to study in this environment. And it is critically important that regular maintenance of your instrument is basically what helps restore it to those original specifications. And so right now, we currently have 2 service locations. One is based in Bellevue, Washington, and the other is based in Kempten, Germany. So what does service really look like? What happens from the beginning to the end? So the very first thing that happens in our process is you take out an RMA, and this is just where you tell us, hey, here's your shipping information, your billing information, the instruments that you're sending in. We have an incredibly wide and varied product portfolio, so it's important for us to know what you're sending in and what quantities. And this is also where you can indicate any particular problems that you've noticed or something odd that's going on, or additional work that you want done. If you want connectors swapped to a different type, for example, this is where you would note it is on that RMA service request form. Then you ship it off. And the next step in the process is really where we kick off our evaluation. So we have 2 steps. One is called check-in, where we're taking a look. I'll go through that in a second. Taking a look at what's arrived. And then we actually have a calibration step. We frequently refer to it as a post-cruise calibration. So the instruments have been out, they've been on a cruise, they've been used, and now they're coming back. But this is actually a critical diagnostic step for us, and it can be really valuable for data correction because sensors drift over time, and that drift is correctable. So it's an important measurement and diagnostic step for us. So the check-in process here, here's an example of what this could look like. You've got a CTD here that's arrived in a crate. First thing we do is check what's arrived against what you've put on the RMA form, just to make sure that everything that you said you were sending in is actually in the box. There's no extra sensors. There's no additional things that we need to take care of. And then we make sure we're entering and tracking that information in the database that we use to track customer-owned equipment. But the first thing we do is just a set of bench checks to make sure that instruments are functioning, we understand what we've got, what we're looking at, and then we actually separate the built CTD system out into its individual components because we service and calibrate them separately. So after we do that just initial check, we know what we've got, then we really start the process of digging into each individual instrument. So this is Toby at our facility in Kempten, Germany. He's taking a look at a 9. And this involves visual inspection. We're looking for anodes that are damaged, scratched or damaged housings. we're interacting with the unit. So doing those basic bench checks of functionality, and then also taking a look at O-rings, sealing surfaces, things like that. If your instrument has pressure, I don't think you guys can hear this sound, but I can. I'm going to turn that down. There we go. So pressure calibration. If your instrument has pressure, then we perform this work, which is actually a characterization. So we don't do a true pressure calibration. We use a digiquartz reference. So that digiquartz sensor is what we're relying on to tell us the true pressure that we're creating. And then we have a couple of different systems for creating pressure. The one that we're demonstrating here is a dead weight tester. So we're actually physically adding weights to achieve a specific pressure. And then we compare what the digiquartz reference is telling us that pressure is to what your instrument is reading. And we'll take a number of different points along the entire scale that's appropriate for that specific pressure sensor, and then generate coefficients, correction coefficients, so that when you get your instrument back, the pressure is reading exactly as it should. The next step in the process is temperature and conductivity calibration. So what we're looking at here, again, is our lab in Kempton, but it's very similar. We have baths that are calibration baths that are a proprietary design. So we've created these and used these for many, many years. But the idea is that we have either natural seawater that we collect off the coast of Hawaii. So some instruments are calibrated in true seawater. Other instruments are calibrated in a saltwater brine. The large baths there, actually the saltwater brine. And we will load multiple instruments into each bath. The bath has a temperature and a conductivity reference that's inside of it. And we typically run the baths overnight. So they step through a number of different points along the temperature and conductivity range that is typical in the ocean, and collect data overnight. And at each calibration point, we're doing the same thing. We're polling the reference and saying, what is the actual temperature today in this bath right now? What is the actual conductivity? And then we're comparing that to your instruments. So again, this step is important. If there's anything that is not performing well about the instrument, this is where we're most likely to find it. That is a really tightly controlled bath. It is capable of maintaining temperature to 100th of a degree C. And it is extremely helpful, even more helpful than something like a thermotron or anything that we can do in air or on the bench. For understanding, is your instrument still performing precisely the way that it needs to? So this is typically the step where we would find subtle problems in terms of your instrument's performance, or larger problems. The big ones sometimes manifest and are obvious. You might have called them out, but smaller problems need this type of instrumentation to really view and understand. So we do expect our sensors to drift over time. So typical temperature drift is 0.2 of a millidegree C per month. And then pressure is anywhere from 0.018 to 0.05% of full scale per year. Connectivity and oxygen also drift. That tends to be different per product, so depending on what you've purchased. But the main thing I wanted to call out is that connectivity and oxygen drift can be episodic. So there are temperature will just kind of truck along and drift over time. But for connectivity and oxygen, there are certain events that can cause an abrupt change. So both of those sensing elements are sensitive to fouling or surface coatings. And so depending on what your instrument is actually exposed to in the environment, there can be a sudden jump in its response. So these pre-cruise calibrations indicate the state of the sensor after the data was collected. So when you get a fresh instrument, either freshly back from service or you've newly purchased it, you have a set of these pre-cruise calibrations, and it's just the state of your instrument. The way it is today. You can go and use it, and then when you send it back in and get the post-cruise calibration, it really indicates how much that sensor has changed over the time that the data was collected. So if there is a slope change or an offset change, either of those can be added to your calibration coefficients to correct your data. And we do have a couple of sessions later on in the week about using moored and profiling instruments, and we go into a little bit of that data handling later. So the key important thing about calibration is you have to know it's right. The whole process kind of hinges on, I've got a reference in the bath and I'm asking the reference, what is the temperature? And then I'm comparing your sensor to that. So how do I know that the reference is really telling me the truth? How do I have assurance that the temperature really is what the reference is saying it is? And so in order to get at that question, we maintain our own metrology lab. So we maintain primary and secondary standards that we use in our calibration work. So for temperature, for example, we have two main things that we use in our temperature metrology. We have a triple point of water cell. So if you zoom in a little bit, you can see Laura is holding this. It's a closed glass system, and you have water, and then you can freeze around it. It has a deep well that goes down. You can freeze the water, so you have ice, you have liquid water, and then it actually has a little cap of water vapor. And the thing about the Celsius scale is that it is all tied to chemical phenomena. So by definition, if you have liquid water, solid water, and water vapor coexisting, by definition, you have 0.01 degrees C, and that is a very useful temperature for pinning any kind of ocean work that you want to do, because it's very closely related to temperatures that we measure. So you got one good point there. The other point that we use is a gallium melt cell. So it's very similar. It's a closed system, but it's only two phases. So you have just a slug of gallium metal. And gallium is a very interesting metal, if you're a nerd, because it melts at a relatively low temperature. So we put it in a little oven, and essentially what happens is it will heat up, and then as it's changing phase, as it's going from a solid to a liquid, the temperature plateaus, and it plateaus at 29.7646 degrees C, which again is super useful because we're really looking at things from -2 degrees C to 35 degrees C. So anything in that range is helpful for us. So now we've got two solid points. But we only have two. So how do we get all the rest of the points? And what we use is a transfer standard. And so we use a platinum resistance thermometer. And platinum is a great metal because it has a very linear temperature response. So we have these two pins, these 2 points that we've pinned the temperature at. We've created those temperatures, so we know that those are real. And then we use this platinum resistance thermometer to interpolate and extrapolate to get to that full ocean range that we're looking at measuring. The only problem with a platinum resistance thermometer is that it is very delicate. And so we use a secondary transfer standard. So after we have calibrated our platinum resistance thermometer in those fixed point cells, then we actually go ahead and calibrate a set of SBE3 temperature sensors that we have sub-selected because they demonstrate very low drift. So these are very solid sensors in terms of not moving. They're very, very stable over time. So we calibrate those to our platinum resistance thermometer, and now we have traceability all the way back to our NIST standards of those fixed point cells. And then the nice thing about an SBE3 is that it's incredibly robust. So if I knock into it or I drop it, I don't want to drop it, but if I do, I'm not going to change its calibration. It will continue to function exactly the way that it should. And so that makes it very useful for putting into different baths, moving between different floors, and actually doing the work of calibration that we have in all of our different labs. The connectivity standard that we use is the same one that oceanographers use throughout the world. So OSIL, standard seawater, and a guild line autocell. And so what we do here is we standardize the autocell using the standard seawater. So we are sure that we are reading, that the machine is reading correctly. And then throughout our calibration process, we actually draw water samples from the bath, and we will take those water samples and run them through the guild line autocell, and that's how we understand exactly what the salinity was during that time, and we back calculate to get the conductivity. So by changing the temperature overnight over the course of the calibration run, we also change the conductivity reading. And so we're able to grab different conductivity points and calibrate your conductivity sensors that way. We also maintain oxygen standards. So we use Winkler titration for our oxygen standard. So same kind of deal. We have a set of reference units that we calibrate as transfer standards. We will put them into our oxygen baths, which step through a variety of different temperatures and different oxygen saturations. And as they hit those different points, we actually grab a water sample. We fix the amount of oxygen in that water sample, and then we titrate it out. So that we'll compare that truth of how much oxygen was in the water to what the sensor was reading correct. And then we use those stable sensors as our references. And we have a program of periodically refreshing those references. So making sure that they're not drifting, they're not changing over time, and that we are periodically calibrating them back to those traceable standards. The other lab that we have is for pH. So for pH, we use a spectrophotometer, and it is calibrated with a purple dye, but we have the ability, again, to draw samples over different periods of time in the calibration run, and use the spectrophotometer to tell us, okay, what exactly was the pH, and then we compare our target sensors to that truth. We're also working on building out our calibration rigor on the optical side. And we have a regular program of sending benchmarking units between our labs. So we have multiple labs throughout our buildings in Bellevue, and then we have our primary calibration facility in Kempten, Germany. And we will send instruments back and forth between those sites, those baths, those rooms, to make sure that every bath is working the way that we anticipate. The goal is that you as a customer shouldn't be able to tell where your instrument was calibrated. It should be the same truth regardless of where that's happening. Okay, so that was a lot of work that we did up front. And now we get to the place where most people, when people are thinking about service, this is what they're thinking about. So this is really the diagnostic and repair and testing functions. So our technicians are, again, trained on a broad swath of our portfolio. And their main task here is to really go through the test data. So they're performing different tests. They're looking at those calibration results. They're interpreting those results and determining are all the sensing components working the way that they should? Are they drifting the way that they should? And then making any repairs that need to happen. They may also be conducting specialty tests. So in certain scenarios, we may have a situation where an instrument is behaving in a certain way in the field. And so that may look different than the tests that we typically perform in our lab. So occasionally we have to perform extra tests to be able to stress the instrument in the exact way that the customer says is potentially causing the problem. So again, this step can really run the gamut. It can be everything from just cleaning things up, replacing labels, replacing anodes, to cleaning and replatinizing the conductivity cell, replacing the temp probe, replacing the pressure sensors, performing any upgrades. Those are all captured in this step here. So this is Bettina, who is working on an SBE9. But again, the repair work could involve anything that might be mechanical, electrical, or could involve replacing any of the sensors. After we do that work, so once you breach the pressure housing of an oceanographic instrument, whatever we've done in there, no matter if it's a little bit or a lot, we want to make sure once we reassemble it, that we have confidence that we've put everything together properly. And if we have replaced any materials, we want to make sure that those materials can go to their rated depth. So after our repairs are performed, we do a pressure test where we reassemble everything, and then we do 2 sets of tests. One is at low pressure. Low pressure is actually really good for finding leaks. So if there is a problem with the O-ring, if something has been misassembled, a low pressure test is going to reveal that. Then we do a high pressure test. And the high pressure test is, again, to really check the integrity of the materials and anything that we've repaired, just to make sure you can go all the way to the depth that your instrument's rated at, and you're not going to be having any problems. After that, it's one more trip through the calibration. So a lot of our equipment, once you do open that pressure housing, you have and make changes, whether or not it's soldering or just exposing boards to different air. That can be enough to change some of our the way our instruments perform in terms of their accuracy. So it depends on what instruments you've purchased, but that final calibration is, again, that final confirmation step that any repairs that we've done, yep, we've got a new sensor in there, it's performing well, it's performing as expected, and this is what generates new coefficients that you'll use for your instrument going forward. And then the last step here, so it depends again on what equipment you own, but the last step is often reassembling systems back into their final configuration. So the individual sensors have been repaired and diagnosed and recalibrated, and now it's time to bring the whole system back together and test it as the integrated system that you actually use. So here's an example. So you've got the 9 Plus. It took its own path through service and calibration, but then this particular one also was equipped with an eco sensor, had an SBE 43 oxygen sensor, temperature, conductivity, and a pump. So it's important that after those services have been performed, everything gets put back together. And then we do a final test. So this is a dynamic check that, again, that integrated system performs exactly the way it should. So this is a dunk tank, essentially. It's salt water that we keep at 2 degrees C. And so what we're checking for is we want to make sure that as we take an instrument from room temperature, or a system from room temperature down to how it's going to be used when you deploy it overboard, that all of those individual components are responding appropriately and playing nice with each other. So after all of that is finally done, then we start the process of repacking that for shipment. We'll send off a final quote, arrange for payment. get those service reports and any paperwork together, and then close the RMA and ship it back to you. So we are always looking for ways that we can improve our service. And so some of the feedback that we've heard is, yes, there's a lot that happens, but it's also taking too long. And so we recognize that, and we want to make sure that we are constantly doing the right kind of changes to be able to improve upon that. So one of the things we discovered is we looked into what are we doing and what's causing delays, what's causing problems for us and for you as our customers. We realized that we had a weird spot that we were stopping the work essentially in between when we were diagnosing instruments and actually doing the work to repair them and send them on to final calibration. And so what was happening here is that we had a instrument that was an entire package, and we could do some things in some places and needed to send other things to other places. So for example, a CTD that was sent into Kempton, a 9+ that was sent into Kempton, we would be able to handle the repairs of the 9, the 3, the 4, and the 5, all there in Kempton, but we would have to ship the ECO to Philomath, Oregon, and we would have to ship the 43 to Bellevue, Washington. So one of the things we recognize, and this is true, even if you send it to Bellevue, if you had an ECO on it, we were sending that down to Philomath. And so one of the things that we have changed this year is we have consolidated our US sites. So instead of having repair and recalibration facilities in 2 places in the US, we are now under one roof in the Bellevue, Washington location. So this cuts out weeks of time, just even transit time, as you have to ship a sensor down to Oregon, have it be worked on, coordinate it back in time, get it back to Bellevue before you can reassemble the system. We have taken a lot of time that's just wasted essentially out of the whole process. Now we're just in the next building over, so it's much handier and much more efficient. The other thing that we're doing, very excited about, is we're expanding our services in Kempton. So this year, what we're focused on is getting the oxygen repair and recalibration going. So we expect to have that capability at the end of Q4. So very excited about that. The other thing we discovered as we looked in here is we had another place that we were stopping, which was between when we actually finished the work and when we were shipping things out to customers. So when people think about the service process, they think about it in kind of this way, where we've got the instrument. We would do some repair or do some diagnosis, and then we would actually, in some cases, have to get approval to perform those repairs. So we would send out, try and reach customers, try and reach end users, get that approval, and in the meantime, the instrument is just sitting there waiting. So by the time we get the approval, then we have to shuffle it back in, put it back in the queue, actually do the repair and continue the process. And then we had the same thing happen at the very end where, okay, we're finally done with all of the work, but based on what actually happened to the instrument, different things happened than maybe that were included in our previous standard service. And so now we have a final quote that's a different amount. We have to wait for that payment. We have to communicate, wait for that payment, and then we can finally pack it up and ship it. And all of that really expands the amount of time that customers are without their instruments. And that's the important thing. We want to try and get the instruments back into your hands as quickly as possible. So this is not the way that we wanted to continue doing things. So what we have done, and we went live with this in July of this year, is we restructured our services to be more comprehensive. So we took a look at the services that would typically be performed within the first 5 years of ownership. And we took a broader view about what we need to be able to just go ahead and do, because 95% of the time, those repairs were being authorized, And most people are shipping things in because they want us to fix them and repair them and get them back to them. So this restructuring means that that at the very beginning of the process, when you send in your instrument, we're going to send you a pro forma invoice that essentially is, we're going to fix it. The vast majority of the time, we're going to fix it. If it's a typical kind of repair that would happen in over the course of normal ownership, we're just going to take care of it. So no longer is there going to be this stopping and waiting and shuffling and reorganizing and nope, just you could diagnose it, fix it, put it back into Cal, get it all the way through the process. The other thing that this allows is because you have the information up front about how much it's going to cost. A lot of folks have their own bureaucracies that they have to navigate when it comes to securing payment or securing POs. You can kick that process off at the beginning. So we're doing the work, you're getting the payment, and now we're matched in time so that when the work is done, we're able to just pack it and ship it and send it to you. And we are seeing as orders go through with this process, we're seeing a dramatically shortened amount of time that, again, you, the customer, are without your instrument. So, so the one ask that I would have is as you're seeing those pro forma invoices come through, treat them as you would have treated a final quote. And again, kick off your process, your payment process, because again, if we can get to that endpoint where we're done with the work, but we've got all of the billing information, all of the shipping information, we're waiting on nothing, then we can get that back in your hands a lot faster than we have been. The last improvement that we have been working on this year is a new facility that we are putting into China. So China is increasingly contributing to the world data set, and it is critically important that they have access to the recalibration services that they need in order to ensure that the data that's being collected meets the scientific community's accuracy standards. So we have a facility that is being built out in Shalu, and we expect it to be up and running and certified in Q1 of 2024. So I'm very excited about that improvement. All right, the fun doesn't end there. We are continuously looking for ways that we can improve service, that we can do things better. We have lots of VOC, voice of the customer, experiences that you guys have shared and ideas about things that we're going to target for 2024. But wanted to share a little bit of what we've been doing this year, and then open the floor for questions.
So everyone, you are welcome to enter your questions in the Q&A box. If that isn't working for you, go ahead and raise your hand and I can give you voice access. But it looks like we already have one question. If a technical support case number is entered in the RMA form because of a known issue, does this change the steps in the service process?
Yes. So the idea with entering that information in the RMA is that then we ingest it and we can make that information visible to the technician who's working on it. So the intent is, hey, we want a very close communication between the tech support ticket and the service technician for a couple of reasons. One is that it could save the technician time, right? If they know up front that hey, this particular instrument is seeing this kind of issue. But then the other thing that is important for keeping that line of communication really tight is those cases where our standard service process might miss what was going wrong for that particular instrument. So so yes, the idea is that technical support number triggers our technicians to work with the technical support person who's been helping on the case to figure out, okay, what do we need to do in order to understand, diagnose, or check or test this particular instrument based on what you've been seeing.
Great. Did we get any more questions in here?
Okay. Oh, wait, one more.
Oh, couple. Um, Concerning the PRTs, do you build them in-house or do you purchase them from another company? And then the second question,
Concerning the
sorry.
platinum resistance thermometers, PRTs, is that right? I'm assuming that's what. If
Yes.
that's not right, put it in.
Yeah, looks
Put
like
it
he responded. That is what he's referring to.
we do not make them in-house, so we purchase them.
And then the second question Thomas had was the element gallium was mentioned. Could you expand on gallium and gallium applications within Seabird?
That is our only application for gallium. I just love it. I don't know if any of you, there's a book called the Disappearing Spoon, and it's just kind of a history of different chemicals in the periodic chart, and it's a very good read if anyone is interested. But gallium metal is just an interesting metal because it melts at such a low temperature. It's just a temperature that's very achievable. So the disappearing spoon refers to like a trick that scientists would play on each other where you made a spoon out of gallium, and then just by like putting it in your tea, it would totally melt. Which I guess was high humor in the 1800s, but whatever. But as far as Seabird goes, no, the primary use of it is as that second fix point in our temperature metrology. So we just use the gallium melt cell. I actually don't know if there's a triple point of gallium cell, but we get what we need. We get that fourth digit of accuracy out of just the gallium melt cell. But that's the only use that we have of it so far.
All right. And then the next question is, what is the pH dye you are using for calibration?
I was worried that someone was going to ask me that. I don't remember, and I will find out for you. And I will let you know. Did they drop their name in the Q&A?
Yeah, I have the name and I'll send you the email. All right, and then do the eco triplet fluorescence sensors drift, ignoring biofouling?
So what I don't know the full answer to that. But what I do know is that we are actively working on improving our calibration, our optics calibration, including the fluorometry, from a characterization to something that is more a true calibration. So it's traceable to a standard that will help us understand individual sensor drift. But I'm not familiar with the details of that, but I can put you in touch with our optic scientist who is familiar with those details and can tell you where we're at.
Great. All right, next question from Francisco. Do you perform pressure performance for all your sensors? Does pressure affect the performance of different sensors? I usually observe a difference in salinity and oxygen from the downcast and upcast.
Oh, all right. That's a big question. So the pressure work that we do. So if your system has pressure, we do a pressure characterization on the pressure sensor itself. So not necessarily as a full system together, but the part of your instrument that has pressure, that's what's being tested. Depending on your instrumentation, we do also perform those at different temperatures. But it depends on what you've purchased and how it's specified. So if you have a specific question about your system, go ahead and reach out to tech support, and we'll hook you up with, again, the science team and help you work through what you're seeing on the data side. There can be small pressure effects, but they tend to be within our specifications.
All right, and then our next one is, when will RMA updates online be accurate?
Yes, totally fair. So we're working on two things. One thing that we're working on is so the way our RMA updates work right now is irrespective of how many instruments you send in. So let's say you send in 10 microcats, wherever they are in the process until they're all past one of those milestones. The information tends to remain the same. So, for example, if 9 of them are completely through final cal and done, and one is still in repair, the whole order shows that it's still in repair. And we recognize that this leads to more questions than answers. So it's not the informative tool that we want it to be. So one of the changes that we're working on is actually being able to see the status of each individual instrument that you've sent in, so that you can see how they're flowing through the system and the differences between them, which also gives you more choices in terms of, hey, I want this back on a certain time frame, but I can wait longer for these other ones, and can help you navigate that. So that's a change that's in work, but it probably won't go live until 2024.
And then we have someone wondering if there is seasonality in our service cycle. Do we see more demand during certain times of the year? And what is our current typical service lead time?
Good question. So we do see seasonality. So typically, we start to see folks pulling instruments out of the water and sending them into for service, Q3, end of Q3. And so we really see a ramp up in terms of number of instruments in-house, Q4 and Q1. And then things are slower, I think, as people are doing more field deployments and are out, at least in the northern hemisphere, during Q2 and Q3. So generally we're going to be busier, kind of starting this time of year through about the March timeframe. The other change that we've been working on, it's not live yet, but it's going on behind the scenes, is getting more dynamic lead times. So what we do have is on our RMA form, there's a page where you can see typical lead times, but there is a lot of difference that I'll recognize in terms of those numbers and those seasonal changes. So as we get busier, what we've started to do more often is to update those to be a little bit more reflective of our true lead times. We are working on a few particular product lines that we know are not being serviced in the right time frame. So we're trying to give a more accurate picture of what those are, and we're updating them more frequently. But the goal in the future here very shortly is to have more dynamic lead times so that you can actually see, hey, at this point in time, this is how long it's taking us to service a microcap, for example. And so maybe this is a good time to send it in, or maybe you would choose to wait. So more accurate information about our true lead time today is coming, not just that typical lead time that you can see today.
Excellent. And then our next question is about Seabird oxygen sensors. It says you changed the equation from Owens-Miller to a Seabird equation in 2008. Are the data before and after 2008 comparable?
I do not know the answer to that question. So I will happily get you in touch again with our science team. That was actually during my time at Seabird, so I'm racking my brain here. But I don't know. I'm not familiar with that. So so let me research that and I will get back to you. Typically what we've done, I do know this for temperature. So when we switched temperature scales, we provided coefficients in both for a while. And so they may not be directly equivalent, but we allowed people to use ITS 68 versus ITS 90. And so I would have assumed that we had a similar option for oxygen, but I will look into that and get back to you.
All right, and then Holly is asking, what is the service process for 5T pumps?
Service process for 5T pumps. So typically these are not calibrated. So at least not in a temperature bath. So what we do is Service will typically involve O-rings, thrust washers, making sure that nothing's binding or sticking. And then we do make sure that the volume that the pump is designed to emit is in the right within the right specification. So we don't want a pump that's suddenly moving too fast or too slow. And so we do a check to ensure that, again, our pumped flow is very important to our system. So we want to make sure that those are well tuned. But they don't spend any time in our temperature connectivity baths.
All right, and can we assume the drift is linear, and is it appropriate to adjust our data based on the drift you detect, or do we use the drift to establish error bars?
So it does depend on what you're doing, but drift tends to be linear. And so it's either a slope change or an offset. And again, we have a couple of sessions coming up here that dig deeper into data and data corrections, and can specifically go through that with you and the instrument that you have and the parameter that you're trying to correct.
Excellent. Are you working on developing a Bluetooth communication capability for your devices rather than only communication cables for communication with computers and field tablets?
So yeah, our communication protocols are something that are under review. I don't have any timelines to share or anything like that, but I can say it's something that we are actively looking at, all of our communication protocols.
Excellent. Right, and then we have another question from Thomas. Earlier this month, I was quite surprised to discover that a packet of salmon came from super remote waters off of Alaska. Do you know of any ocean exploration and/or commercial fishing operations out in that part of the Pacific? What generates the science need or wants out there?
Oh, that's fascinating.
Question.
That is a great question. No, I do not. I am not particularly familiar with the science that might be happening there. And I can only speak sort of broadly as to what kind of drives the need. And it really runs it runs the gamut in the sense that we serve customers who are doing conservation work. We serve customers who are doing hatchery and fisheries work. We serve customers who are doing oil and gas work. We have our research scientists that are working. We have our climatologists. So there can be a lot of different reasons why people are interested in particular areas of the ocean, but I'm not familiar about that one in particular.
And then Robin is asking, even if we don't notice any drift in our sensors, should we still send in our equipment to be checked and repaired after every field season?
So best practice is to evaluate the use of your sensor against the data need that you have. So and it's very application dependent. So some folks are using their equipment rough. And you can tell, you can look at it and you can tell. They're using them in high fouling environments. They're using them in just difficult to control. So they're seeing a lot of physical interactions. They're seeing a lot of biological interactions, and those would be applications where we would recommend more frequent maintenance. And then but it depends. So again, those highly accurate data sets, that's where we've got people who send it in pre-cruise, post-cruise every time. Other folks are kind of on a 1-year cadence. I would recommend not waiting longer than 2 years between servicing, just to make sure again that some of the parts of your instrument that do see wear and tear are getting some regular inspection and replacement.
And then we have someone asking what the repair process is for the 39 IM or 39 PIM.
So it would be very similar to what I showed here. So there are bench checks that we would do on every 39 coming in. Then we also occasionally we have requests for downloading data or preserving data. So that's another good thing to call out on your RMA form. But we have bench checks, and then if it has pressure, it will go through that pressure characterization. If it doesn't have pressure, then it goes into, it's a temperature only bath. So it's a smaller bath than the one that you saw in the photo. But we can control temperature even more tightly the smaller that it is. And so, but it's the same idea. It will run through I think it's 10 temperature points, 10 or 11 temperature points over the course of the evening. And that bath has a primary and secondary SBE3 reference inside of it. And both of those instruments will have been calibrated against the platinum resistance thermometer and have traceability to those fixed point cells that are NIST certified. But the target instrument, your instrument, will be pulled on an IM line. And so we check the communication, we check that everything is working properly, and that it's reading, whatever temperature it's reading at whatever temperature point, we compare to the reference and then generate your new coefficients based on that. And again, temperature, we would typically see an offset in drift. It's not very slopey. It's across the whole range. It moves.
All right, and then we have a customer from Cyprus with a couple of questions. They say they have the 19 plus, and they've always sent the equipment to the US for calibration through our local representatives, and it's taken about 4 to 6 months. The questions are, when will the Germany office be fully operational for repair and calibration for all sensors, the SVE19, ecofluorometer, turbidity par, etc.? And then do we need to send the equipment through your representatives, or can we do it ourselves?
Okay, so multiple questions there. So currently the Kempton facility is able to handle 19s and some of the associated sensors. Again, the capability that we're building out this year is in oxygen. But the next thing we're going to work on is the biogeochemical side. So being able to handle some of those eco sensors. But we don't have specific plans in place, so I don't have a timeline to share, but that's definitely the next kind of expansion that we would consider for the German team. And then typically sending items in through your rep is what we would recommend, depending on what additional parts and depending on your system specifically. So if you want to reach out, I can answer again depending on what you have and how it's set up. We can see what the right thing for you to do in order to shorten that time frame, because I recognize that's a long time to be without your instrument.
Great. Looks like that's our last question. Give people another minute or so in case there's any more coming in, but if not,
if something occurs to you, or if you have a specific question about your order, your equipment, I realize it's hard to speak in generalities when we have such a breadth of instrumentation and configurations, and some of the answers are going to be very specific to what you have. But feel free to reach out to service. Feel free to reach out. That's just service@Seabird. You can also reach out to tech support. And then those of you who asked specific questions that I didn't know the answer to, Nicole's going to help make sure I've got your names, and I'll reach back out and get you in touch with the people who do know.
excellent. Thank you, Genevieve, and thank you everyone for attending. As she said, please reach out if you have any other questions. And if you have a minute, please take our survey and give us some feedback on this after the webinar. So thank you.
Thank you very much.